Afternoon, everyone. I hope I am okay. Good afternoon, all. Okay. So today our session is on comparators, priority encoders, and sequential circuit basics. Okay. So with comparator and priority encoder, we will conclude the combinational circuit. Then we will see something on the sequential circuit basics. So you can get an idea about it. Okay. So anyhow, in the whatever the thing in the real thing it is happening, that has been converted into a logical stuff, and that they made it on a hardware so that the hardware can do and make decisions. So for that, something if you want to take decisions, you have to compare whether this is greater than or that is greater than. Okay, so it will always happen in the uh, real time scenario, and same thing is happening, and the same thing they captured in the programming, whatever the thing which is coming in the automation, no? Those things they were trying to capture it. So a comparator, it is a combinational circuit, so it's also a combinational circuit. It is used to compare two binary numbers. So why it want to compare the binary numbers? Because the digital system works only in the binary numbers. Okay. So this comparator will try to give whether A is greater than B, or A is less than B, or A is equal to B. So these three things, only with these three things it will try to compare it. So output generally A greater than B, or A equal to B, or A less than B. So it is used in the arithmetic logic units and address comparison when we try to compare the two addresses. And if you want to sort the hardware, we want to compare it. And decision making circuits, this is something, it comes under the decision making. Okay. And the digital control systems. So digital control systems. So in these things we will be using these comparators. Okay. So what that one bit comparator is going to do, what this one bit comparator will go and do the things. Okay. It compare A and B because it is one bit. So truth table, it will try to compare. This is A is 0, so it is checking A greater than 0, no. A equal to 0, yes. A less than 0, no. So this is what we are going to write the truth table, and from that we will try to get an Boolean equation. So if it is greater than, equal to, less than, and we will try to we will combine these things and make it as a comparator. That's it. So it is a simple example, but these simple examples are very much important. So you guys, we want to work with these simple examples. So with small thing, we can able to build a huge block of stuffs. Okay, so that is the idea behind it. In a multi-bit comparator, where we can go on to compare many bits, like a single bit you can go on to compare many bits. How it is going to compare? So it will compare, we have 4 bits and we have 4 bits. Okay, so these are two numbers which is having 4 bits. This is LSB, this is LSB, this is MSB, this is MSB. So how it is going to compare? It compare first the MSB. It starts from the MSB. Okay, it starts from the MSB. Okay, if MSB differs, then the decision is made immediately, because MSB is the most significant bit. With the help of this MSB, we can tell whether this is greater or less or something like that. We can go something. If it is different means you can cleanly tell that whether it is greater than or less than. Okay, so for equal to only we want to go through all next bits. So if this is greater than this, then if it is differs, then easily we can go and compare the things. So you usually it starts from the MSB. Okay. So for example, 1010, if we try to compare 1001, MSB here it is 1, and then this MSB is 1. Okay. So it is equal to, then it goes to this thing, and this is also equal to, then it checks this one and this one. So now it will come to a conclusion that, okay, this is greater, so this is one is greater than Joe, so it will tell that A is greater than B. So that is the idea. Okay. So it is used in magnitude comparison and also in ALU operations, branch decisions. This is very much important. And sorting the circuits, digital measurement systems, everywhere this comparators is used. So that's about the comparator. Then we will try to understand something on the priority encoder. See, we learned about the encoder. Yes, uh, you have many 8 to 3 encoders. So we have the 8 and it will convert into 3 bits. But there are, if we have multiple inputs with high values, okay, so we want to give some priority to those stuffs. So that is where the priority encoder comes into a picture. So the priority encoder is as a combination circuit that encodes multiple active inputs into binary output and giving priority to the highest order active inputs. So in the normal encoder, the problem is if multiple inputs are high, okay, we know that for the encoder, we will go on try, and we will, for an 8-bit encoder, we will, if this is this value, this is the stuff. If this is this, so if we have multiple inputs having one, and how we are going to handle that? Excuse me. So it will give an ambiguous input. So the priority encoder, it will go and solve. Okay. So we have D2, D1 and Y0, Y1 and Y. These are the outputs, because depending on this, whether to select this, and it will go and combine it. So here what it is taking, it's the priority. That means if D3 is 1, D2 is 1, it gives first priority to D3. So, if meaning D3 equal to 1 means output corresponds to D3, even if other bits are I. Even if other bits are I, the priority encoder will go and give the priority to the D3. Okay, that's the a small a small thing about the priority encoders. So if you see truth table, okay, lower I and the most significant bit, okay. So this is the LSB, and this is going to be the MSB, okay. So when all the bits are 0, the output is this Y1 is don't care. It is don't care, and no, it is not. Okay, we are not, because everyone is 0. So the encoder no need to do anything. Okay. Suppose if the LSB is 1, it is valid. So Y1 and Y0 is 2. Okay, something like this. Okay, for this 0 we are making this one. For this one we are making it this. For 10 we are making it this. For 11 we are making it this. This is where the normal encoder, and we will try to put 0 over here. Okay, but here you try to understand this. If this is the case, it is 1, correct? But if D1 is 1, whether this D1 is 1 or 0, not at all a problem. They will give the valid as 1, because this D1 is 1, so it is giving the priority. And if D2 is 1, whatever the value, whether it is 1 or 0, it is don't care. It will not care. It will go on to give the, because this is very much important to the priority. It goes and gives this as an output. And likewise, this is the idea behind the priority encoder. So something like interrupt controllers, keyboard encoding, resource arbitration. We can tell it as an arbitration, because two things it want to go on to take single stuff. So there is an arbitration, there is a fight. So in order to avoid that, they will give the priority. Okay, among the students, you all have the same priority, but in the student group, if there is a leader, the leader is having more priority than the other students. So it is something like that. And bus request handling, and for processor exception handling. Exception is nothing but the interrupts. Okay, so in these things, they will go and use the priority. So wherever you will see that the priority comes, they will go and use these priority encoders. Okay, so that's up to this, we are giving an full stop for the theory part of the combinational circuit. Okay, I am giving the full stop for the theory. Still now I was looking into only the theory part of the combinational circuit. Okay, so from this onwards, we will try to look into the sequential circuit. So until now, the combinational circuit, what it is doing is, in a crux, we can tell that the output depends on the current input. The output is going to depend on the current input. That's all. When the current input changes, output changes. That's it. Nothing. There is no storage element. There is no feedback. All these things. So that is where the combinational circuit. But this combinational circuit, with this, we cannot do much. We cannot implement many designs. So they went for, why can't we try to give a feedback system along with the input, and what it is going to happen with this combinational circuit. So they came an idea called an sequential circuit. They come an idea called sequential circuit. So from this point onwards, we will look into the sequential circuits. So in the sequential circuit, what they are trying to tell is, this is the combinational circuit. Okay, this is the combinational circuit. The output is going to depend upon only on the input. But the sequential circuit, what they were telling is, why can't I go and give one feedback mechanism, so that this is the output you are getting, this is the input. Okay, so I will try to have I will try to store the output, and that output I will give as a feedback, and for the next input, this circuit will work depends upon the feedback, and then the input, the output changes. Okay, so that is what the sequential circuits are, digital circuit whose outputs depends on, whose outputs depends on present input and the previous state, that is the past history. So previously you will be getting one output, that it is stored. So you need some storage element, something like that, and then we will go and put it in that. So the output is going to depend on the present input and the past history, the previous state. Okay, so that means they have the memory. That means they have memory. So in the combinational circuit, it is going to depend only on the input. That function is going to depend on only on the input. But here you see that it is depend on the current input and the previous states. Okay, what is its previous state, and it is going to depend upon that. Accordingly, it is going to give the output. Okay, so this is where the real stuff comes. Okay, so for example, flip-flop is a sequential circuit. This is the basic storage element. Okay, this is the basic storage. Registers, in the CPUs, you need the registers to store it. Okay, they implement through the flip flops. Okay, then counters. This is very much important. Program counters and lot and other in the timers, many things you need. Then if you want to implement a you see CPU is a, if you consider CPU is sorry, it is a state machine. It is a state machine, and particularly they will call it a finite state machine, because the CPU goes from one state to another state, running state, lot other thing. Okay, so it is a state machine. So to CPU is a state machine. To implement that state machine, you need sequential circuit. We need a sequential circuit. Then for the shift registers also, we need the sequential circuits. Okay, these are intro to the sequential circuits. 1 second, guys. Suddenly, I got an sneezing started. Okay, let us consider. So this is the basic structure. We have a combinational circuit, and the output, whatever we get, we will try to store it in a memory element, and that we give as an input. Okay, so this is the stuff. Okay, so still we are using the combinational, that is the basic, but only thing is we are trying to put some extra thing. We are trying to give us some feedback mechanism, so that the output is not always present on the current input. So it is capable of having a memory. Memory means history. It is capable of using the history, and it can do something, so we can have a better output. So we can have a better output. So this is what the thing which we have to understand in the sequential circuits. Okay, this is the difference between the combinational and the sequential circuit. Okay, so if we remove this part, no, it is a basic combinational circuit. But when we try to give the feedback, it becomes the sequential circuit. Okay, okay. So now when we try to give the feedback, okay, so there comes that when we can go and give the feedback, whether it is in controlled way or something, it will go and take it in an automated way. So something they went and used. So there comes two types of sequential circuit. Okay, so anyhow we are giving the feedback. Okay, that is correct, we are giving the feedback, but how this feedback is applied, whether it is applied according to the clock, or whenever we need it want to go on to changes. So that is where this types of sequential circuit comes. Okay, we want to give the feedback, that is sequential circuit, you leave it, that is correct. But how that feedback want to be controlled, that comes the two types. One is synchronous. See, you keep in the digital system, synchronous means clock, something aligned with the clock. Asynchronous means it is something not aligned with the clock, but they will use clock, that is okay, but it is not aligned with the clock. Okay, so synchronized, that means this signal, and I am trying to draw one more signal also. This is synchronized, but when I try to do this and these two signal, it is not synchronized. That means they are not able to go in accordance with that what they both want to go. Okay, so this asynchronous, anytime anything can happen, but here only during the clock changes it will going to happen. So in the synchronous sequential circuit, it is controlled by clock, so only on the clock edges the changes will happen. But here no global clock, so the state changes immediately when the input changes. See here, see, both are having the feedback, both are having the feedback, that is for sure, both are having the feedback. Okay, this one is when there is a input change, the output is changing, that is where asynchronous. But this one, okay, this is also having a feedback, but whenever the input changes, the output will not change. The output will take effect only when there is a clock, and that too if the clock is having, that is edge. So this is the rising edge, this is the falling edge. You can configure it whether you want to do it in falling edge or right edge. So whenever the clock triggers, whenever the clock triggers, that time the output will take effect, that's it. So it is controlled by clock, it is not. Whenever it is the changes, it goes and change, but the change is depend on this feedback. Both are depend on the feedback, that is for sure, that is for sure. But the output takes effects only on the clock edge here whenever the input changes. So when here the clock edge is not, when the clock is not given, when you try to change the input, the output will not take effect. It will take effect only when during the clock edges. So that is where it is synchronous sequential circuit, and this is called the asynchronous sequential circuit. Okay. So I forgot to tell this one. Okay, it is predictable, easy timing analysis. It is widely used in VLSI, CPU registers, counters, FSM. Fast response, but it is hard to design. Race conditions will occur. There is a lot of glitches, so we use less frequently. It is not like we are not using it, but we will use it less frequently depending on your application nature. Okay. So this is the diagram, asynchronous way. Okay, here the clock is given. Okay, here also you will have a storage, that is okay. But when the input changes, and it will take effect from the feedback and the output changes. But here, no. When the input changes, only during the clock edge, the output gets the stuff. That is the difference which you guys want to understand between the synchronous and asynchronous sequential circuit. Okay. So then rest and all theory only. Whatever I told, that I am trying to give you, I am trying to capture it over here. So the memory elements. So sequential circuit requires storage. Okay, it requires storage. Then what is the basic storage elements we are going to use? Latch, flip-flop, and registers. So it will use to remember the previous values. So we will be learning these three things. These three things are, excuse me, very much important for the sequential circuits. This itself a sequential circuit, I can tell. Okay, this latch flip flop itself a sequential circuit. So we will go and see one by one what is latch, flip flop, and registers. Okay, latch. So till now in the combinational circuit, we didn't talk about any something in the circuit. If we give output is there, that's it. But when there is no input, that output is gone. That's all. Output is gone. So somewhere we have to lock that output. Somewhere we want to go and latch that output. How do we do that? That is where the latch comes over here. Okay, so a latch is a level sensitive storage. Output changes while enable is active. Okay, that's a formal definition. Okay, for example, here the diagram gives you some SR latch, set reset. If we give set, output will be 1. If we give reset, output will be 0. So that is the thing where we want to go on to capture the stuffs. So when we going to set, output want to be 1. When we going to reset, output becomes 0. Then hold means retains the previous state. So there is a stuff, but there is a problem with that. There is an invalid state possible. Okay, so here I told sequential circuit is feedback. So they have given the NOR gate, and the output of one NOR gate is given as input to the another, and this output is given as one input to the another. And when they try to give ones and zeros, when they try to give zero, something like that, what it is happening? When both the things are 0, it will maintain the state. The previous thing, what it is there, that is getting maintained. That is where the latch, when we try to give 0. But when we try to give 0 and 1, that means reset. So this Q will become 0 and Q bar is 1. So it is reset. Reset means we want to make the output 0. That is where the reset. Now set. That means we want to make this 1. When we try to put 1, that means we have to give 0 for this. 0 for this reset and 1 for the set. So it will go and set it. This is the output. Now there is a problem. Till this combination, it is good. No problem at all. Till this combination, it is good, no problem. But when we try to give 1 1, you cannot determine how this, when Q is 0, Q bar want to be 1, but no, you will be having some invalid states. You cannot predict this. We cannot predict when we try to make it. See, until this there is no problem, but when we try to give sometimes both the things 1 1, no, then its real problem starts. How we can make set and reset 1? That is the logical thing, but we have given the option. Okay, so that is the idea. So it is having a invalid state is possible. Okay, invalid state is possible. Which one want to repeat it? Which one you are not able to understand? You asked me to repeat, but which one to repeat? I didn't see it. Where you guys having a problem? Just put it in the chat. What you didn't understand? Yes, for everyone it is good afternoon. Which one you are not understanding? Okay, you put it in the chat. Then after the class or something in between, I will try to do the things. Okay. Arsha. Okay, now the flip-flop. So latches, you can use latches, but it is having some invalid states. So they will go on to use that enable and lot other things are there. Even with this, without giving the enable and that kind of steps, it will go on work. That is not a problem. But still the latches, it is level triggered. So during the level, only it will work. So in that level, there is a chance of having the data 1 and something the glitches happens more. So the output, it is somewhere there is a problem with that. So they went for edge triggering. During the edge, whenever only that edge occurs, that input want to go and change and whatever the things occurs, the output will take effect only during the edges. Edge triggering. Okay, either positive edge, only in the positive edge, or in the negative edge, or in the both the edges. It's up to us. Okay, so edge triggered memory element and changes only on the clock edge. It is changes only on the clock edge. So they kept this latch circuit something like this, and they went and added a control circuit and SR stuff, and it want to happen only in the clock pulse. They try to give the clock. Okay, so that kind of things they have. SR flip-flop, JK flip-flop, D flip-flop, and T flip-flops. These are widely used in synchronous design. This is widely used in synchronous designs. So the state concept we will try to understand by having an example. Okay, the state concept we will try to understand by examining the example. Okay. See, sequential circuit maintains a state. For example, there is a door lock system. There is a door lock system. That means if the button is pressing, that is the input. Depending upon its previous state, while pressing the button, the door might be opened. Okay, while at the time of giving the input, the previous state might be door might be closed or locked. I mean, locked or unlocked. Who knows? We don't know about the previous state. So the current input and the previous state may be locked or unlocked. So the output is going to depend upon the current input, whether the button is pressed or not, and the previous state is whether they locked or unlocked. We want to capture all these things. Okay, so now you started looking into the actual problems. So this combinational circuit cannot handle it, so they went for the sequential circuit. See, you guys try to understand this, then the sequential circuit will become an easy step. Okay, so you want to consider all the things. Our previous state might be locked or unlocked. Okay, so the previous state may be locked and the current input might be button pressed. That is one combination. And our previous state, I mean, it is locked, but in the current input, button is not pressed. No button is pressed. The same thing repeated with unlock with button pressed and button not pressed. Okay, so something we are trying to understand the state. Okay, so this is what will happen in the real case scenario. So hope you guys able to understand this current input and the previous state, because with these two only the output is going to change. What is that output? That is the next state. Okay, so the previous thing is locked, the previous state is getting locked. Okay, the previous state is getting locked, and then the button is pressed. So now we got unlocked. That means the mechanism is released. When the previous state is locked and we are not pressing the button, please try to understand, the next state is going to be locked only. Here, since the button pressed, it is unlocked. But here, it is locked only because the button is not pressed. Okay, by these two combinations, they are trying to get it is stays secured. This is what the thing you guys want to understand. It looks simple, but you have to understand. This is the total sequential logic I am trying to explain with one practical examples. Okay. Next, the previous state, I used all combinations and I got the output. This is the output. That is nothing but the next state. That is what they will call it as. Okay. And this next state will become the previous state for the next input. Okay. So I don't want to confuse you much, but this is the idea behind it. Next comes unlocked. The previous state might be unlocked. And when we try to press the button, that means the door is unlocked and we try to press the button, the door gets locked. Okay, so that means the mechanism is engaged. That means the door is locked. The previous state is unlocked and we are no button pressed. The thing will be unlocked only. That means it stays open. So this is what one example of the sequential circuit where the output is going to depend upon both the previous state and the current state. With that, we are deriving the next state. That next state is nothing but its present output. Okay, so this is what the idea behind the sequential circuit. Hope you guys able to understand it. Okay. Next, the thing which you have to understand is timing concept. See, I will revise once. Sequential circuit, it is off with what I will tell. It is off with we have an feedback. Okay, combination circuit, something it with feedback. Next, it is having asynchronous and synchronous. Okay, synchronous and asynchronous. Then that is having a memory, so we need a latch, flip-flop and registers. So we went and looked into what is the latch, something it is holding. It is having some problem. And with that problem, we went and solved by using the flip-flop. These things we will look, but before that, we will try to understand the sequential circuit with some own logic. Now, this is the state concept. The state, next state, current input, the previous state, that you have to understand it. Next, what you guys want to understand is the timing concept, the important timing parameters. I told during the edge, it will, during the clock edge, it is going to delay. So there are some important timing parameters we have to understand. Propagation delay, time for output change after input change. See, to the circuit, we are giving the input, and when there is a change in the input, the output want to take effect. So there is a propagation delay of some nanoseconds that we have to consider it. That is one thing. Then setup time. What is the setup time? Input must be stable. See, I told only during the clock edge the transition will happen. That means that everything is going to change only through the clock edge. So when the clock edge is there, the input want to be stable. Otherwise, how it is going to uh, give the correct answer? So that is where setup time. That is where the setup time. Next, hold time. That input want to be remain stable after the clock edge. After the clock edge, the input must remain stable. That is called the hold time. So these two things are very much important. During the time, the input want to be stable. If there is any change in the input, then our output is something totally stuff, a mess. Next, clock to the Q delay, that is the output delay. So the time between the clock edge and the output response. The clock edge and where the output is response, that is also going to play an important role. So these things we have to consider: propagation delay, setup time, hold time, and the clock to Q delay. You try to understand this. I have a data, I have a clock, and I have an output. Okay, try to understand it. Okay, so I have a data, I have a clock, and I have an output. So I am trying to maintain a setup time. So that setup time, during the setup time, I want to maintain the data. So XX means the data is changing. But here, I am trying to maintain the data. So the data want to be settled before the TS starts. The time, setup time is TS. Before the TS starts, our data want to be get settled. That means the data want to be 1. That means data is nothing but our input. You consider it as an input that want to be getting settled. This is very much important. Okay. Next, during the hold time also, data want to be settled. Hold time also, data want to be settled. So the clock, when the clock edge comes, now the data is something, it is settled, it is there. So output will take care. The output will change. So the output want to also, after, see, till a clock of Q delay, the output want to maintain it so that it will take effect. That is what. Okay, so there is a time, clock to Q delay. This time, after the clock edge, the output also, you need some stable. Whatever the effect it takes, it needs some time. Okay, it needs some time. You see, till T0, there is no effect in the clock, I mean output, till C0. Okay, so the output changes after some T0 time, the output is changes. So that is the thing which you guys want to understand it. So this clock to delay, time between the clock edge and the output response, time between the clock edge and the output, it response. Okay, and then the hold time and the setup time. So these are something which you want to understand it. Okay, so this is the same thing I'm talking about. This is the critical window. Just okay, I captured these things and put it in a critical window. That's it. Okay, so these are the certain rules for the setup time. data must arrive and settled at the flip-flop input before the clock edge arrives. That is what, then why it is matters and everything I have given it here. And data must remain completely unchanged after the clock edge passes. Okay, then the time required for internal data to actually propagate to the output of the Q pin after the clock edge hits. So that means the flip-flop is not instantaneous. This delay dictates how fast the captured data becomes available to the next stage of the logic gate downstream. Now the propagation delay, the time the signal takes to travel through logic gate or a long copper wire, that is where from the logic gates to the output, what is the time it goes takes that signal to propagate, that is what. So in a circuit pipeline, the total propagation delay of a combinational gate between the two flip-flops determines our overall system speed. Okay, so this propagation delay determines our system speed. Okay, so these are something which we have to understand when it going to implement in a practical sense. Okay, so hope you guys are getting some idea about it. Okay, so what is this state transition idea? Sequential circuit moves between the states. So traffic light controller, red is as one state, green is another state, yellow is another state. So the clock moves system between the states. So we can represent this through a state diagram or state table. I will tell these state diagram and state table in the finite state machine. When the topics comes on the finite state machine, okay, I will explain it clearly, but right at the time being, you try to understand one state, it changes to other state and changes to other state, then again changing it to state, something like that. Okay, so the sequential circuit moves between the states. Okay, so the feedback in sequential circuit, it creates the memory and output fed back into the input logic. Without feedback, there is no state retention. So the state want to be preserved with the help of feedback. With the help of feedback, the state want to be maintained. So when it comes to the application of sequential circuit, the processor, communication system, controllers, memory system, finite state machine, protocol engines, counters, timing generators, these and all, whatever the present thing we are using, everything we are using it with sequential circuits. We are using it with sequential circuits. Okay. So this is fundamental for, I told about the pipeline. I will tell you, fetch, decode and everything. No, it will go on to do that. So for that we need this stuff. Okay, and for processor design, control logic, register files, buffering, and for synchronization, for all that purpose, this sequential logic is going to be an fundamental. So in summary, we went and looked into comparator, priority encoder, and the memory element. Maybe in the next class, we will go deep inside these flip-flops. Okay, I hope so. We will be moving into the flip-flops and design. Today, it is only the sequential circuit basics. So these all are some foundations for processor and digital system design. So you want to be good with, sorry, okay, it is not, my mouse having problem. Okay, so you have to be know some knowledge on combinational circuit, sequential circuit, particularly with the sequential circuit with latches and these things. And then with the timing concept is important, but that is easy, you can understand it. First concentrate on these things, then slowly you can go deep inside it and peel the layers, so you can understand, you can have a better understanding. Okay, so that is what about the today's stuff. Okay, so if you guys have any doubt, please let me know and you tell which slide and everything. Someone has been messaged that I have a doubt, I don't understand, but still now I didn't get any reply from them, which thing they didn't understand. Okay. So now you please tell me where you find any difficulties or something. Okay. Please let me know. Still we have 10 minutes for the question and answer. So you can go and look into it. Meanwhile, let me upload the PDF. State concept. Okay, 1 second. I will explain it after uploading the PPT. Okay. See, the state concept, okay, you try to understand. First, I will tell in the combination, you don't have any state counter. The input and output, whenever input changes, output changes depending on the whatever the circuit you gave. So there is no, don't want to maintain any state or something like that. But here, the problem with the, I mean, not a problem, the thing which you have to analyze is something we are giving a feedback. We are giving a feedback, and this output is going to depend on this input and this feedback. Okay, this feedback is nothing but your previous state, and this is what your current input, and this becomes your next state, that is the output. Excuse me. So you have to understand this. Okay, then, okay, this is for this time, this is the current input, and previously there will be one output, no, okay, that is going to be the previous state, and because of this now the output is changed, that is the next state. Is this clear? No, today I am not going to have the EDA or something. I have given you yesterday itself, and for the past 3 to 4 days I have shown you the EDA playground. Okay, so where the same thing, EDA playground and all those stuffs, you can go and work, and you can use the AI tool, go and type some, give me a sequential circuit example for a very log with a test bench, you can go and work it. Okay, so this is about the state. Okay, this is the thing. So now this is the previous state, we have been looked into it, this is the current input, and this is nothing but the output. You for a time being you try to avoid this. Okay, so now at the time of giving input, when the button is pressed, previously it was unlocked, so now the output is going to be unlocked. That will be the next stage, that is going to be the unlocked, and in the continuation of that it is unlocked. Okay, it is unlocked, so now it becomes previous state, it is unlocked, it will become previous state. In the current input, if we try to press the button again, the next state will be locked, the next state will be locked. So in that way, if you try to see the state, it will be easy. Okay, hope you guys able to understand the stuffs. Okay, and then I explained, I told about the practicals, then timing concept. Okay, there is a timing concept. Why it is not changing? Okay, the timing concept, what I am trying to tell you over here is, okay, you leave this propagation and Q delay. Okay, first you try to concentrate only on the setup time. Okay, you see the below diagram, you try to look into the below diagram. There is a concept called setup time. That means what? The data want to get settled. The data want to be get settled. Okay, so the change will happen only during the clock edge. The change will happen in the output only during the clock edge. So before the clock edge, data want to be settled. After the clock edge, the data want to be hold for some time. That is very much important. The data want to be hold for some time, so that during the clock edge, since the data is maintained, their output will come. The output will change, but when it will change, it will take some time to take effect. That time is clock to Q delay. So the data want to be stable for that time also. That is the hold time, and you can call it as a clock to Q delay time. The data want to maintain, and once the output take effect, we want to have some step. The output will not take as soon as the clock pulse is triggered. The output will not take effect. It will take some time. Then the output will go and change it. Okay, that is about the propagation delay. Is when the input goes inside the gate. When the input goes inside the gate, and when there is an output, that is the propagation delay. Okay, I hope you guys able to understand it. Okay, okay, I hope you guys got an idea. Okay, guys, see you. Thank you. See you tomorrow. Tomorrow is no, Monday. Okay, Monday. Bye. See you all. Thank you. Yes, thank you. Thank you all.